Hello folks, I call this a tale, excuse me, I call this a tale of 6 lathes. Each of these rectangles over here is 6 lathes, 6 machines. They each have 3 levers on them, but they're in different positions. Here's another 6 machines, 6 lathes also, but all the levers are in the same positions on the same side of the machine. A lot of shops end up like this. They buy a machine here, they buy a machine there. They may be new, they may be used. Whatever they are, they buy a lot of machines. Let's say they ended up with 6 of them. You've got 6 machines here, each of them different. That's what I'm trying to imply by having my little levers in different positions here. Each one is different, so each one is going to have a different feel towards it, a different way of doing things. Each of them does what a lathe normally does: turn diameters, bore out inside diameters, drilling, thread turning, facing cuts, grooving, all that kind of stuff. They can all do the same operations, but they each do it a little bit differently because their levers and hand wheels and knobs and buttons and everything are in different positions. So you can have an operator over here that is good at running this machine here. You put them on any of the other ones there, it's going to take him a little while to figure out how to run that machine if he hasn't done it before. The learning curve is different. Now, or there is a learning curve, period. Now, if he's a good machinist, if he's been around, if he's got a lot of experience, he'll be able to walk up to any one of these, chances are, and, in due time, figure it out, find out where it's at, where the levers are at and how it all works. Some machines are significantly different from others. Others are, darn near identical. But there is a bit of time spent doing what I call learning the lay of the land. Where are things in this place here? I've got a machine to operate. I've got to run these parts. Where is everything? Where's the lever that does this? Where's the lever that does that? Okay. In this scenario here, all these machines, let's say, whether they're new or used, let's say they are all the same manufacturer and they're all the same model, they're all the same size. Well, what do you have then? You've got all the levers in exactly the same positions, locations on the machines and all that, and they all function the same way. So you take this guy from here and put him on this machine or that machine, there's essentially no learning curve because they're all the same. You take this guy over here and put him on this one. This guy took a day off, put him on that one. You want to run this product over here because that's, closer to whatever, the supply or something like that. Hey, no problem. You can move people and products around very easily and very efficiently because they're all the same. I think you kind of see where I'm going with this. This here is a lot more cumbersome, requires a lot more experience and a bit more time for the guy to get set up and figure out what he's doing. And even if he's run it before, it still takes a bit of time to get reacclimated to that different machine. It's like, wow, I haven't run this thing here in 2 years. How does that work again? Oh yeah, now I got it. And hopefully he kept his own PCB, process control book, and wrote notes on it. So he goes, oh, remember this machine here? You have to do this if you want to get that done. And this is how you get that in position here. Okay, so all fine and good. This here does have an advantage in some ways because a lot of times these machines will have different capacities. So if you've got a really big part, well, give that to this guy on that machine. It'll go real well. These ones here, you're locked into whatever these machines can do. Okay, but there's also a big drawback to this, and that is that on these ones here, they're going to require different parts, most likely, for maintenance. So if the belts go down on this one here, you probably don't have belts from any of these others that'll fit on there. And if you need a gear for this one here, or a key for this one here, or the lever fell off of this one over here, or blew out fuses on this one here, you're out of luck. And you've got to stock the supplies for all of these, or know someone that does, some supply center somewhere where you can get all these things. So maintenance becomes a bigger issue on these here. Now, with these ones here, it's easy to stock all the same belts, all the same fuses, all the same coolant pumps. Anything goes out, we've got it covered. It's no problem. Okay, now, if all of these machines were new, well, that levels things out quite a bit because new machines naturally have fewer problems than used machines. That's what happens to machines. They wear out. But when these machines wear out, this here is going to be a hugely bigger problem than this over here will. This will be a lot easier to work with because you've got more machines, and if you need to, a lot of shops will do this. They'll say, well, okay, these machines are already 20 years old, so this one here that seems to be the most defective out of them, you know, remember the guy that ran that a few years ago? Boy, he really beat that, you know, that kind of thing. This one here might be the one that just doesn't seem to be so good. So what do you do with that? You keep these ones going, and when you need those unusual parts, you cannibalize them off this one here, knowing full well that eventually this thing will be, you'll pick every morsel of meat and every bone off this thing. There won't be anything left, and it's time to get rid of it. But it kept these other 5 machines going, and at some point, you know, you've already figured this into your budget. You've depreciated these things. You've put that money aside. You know that it's time to replace this one, perhaps all 6 of them. And you do the same thing again. You buy 6 identical machines, and hopefully in doing that, you also upgrade the technology to give you the competitive edge against anyone else that keeps your product out there, that keeps it your operation efficient and making the money for you. Now, there is one more little point that I want to cover here, and that is when you look at these, this is only lathes that I'm talking about because it's a simple machine, relatively simple machine to talk about, but it applies to mills and grinders and drill presses and you know, all sorts of things, you know, honing machines and tumblers and deburring machines, you know, everything that's mechanical that we use in manufacturing. So this generally applies to almost any kind of machine. But one more point I want to make is that on an average lathe, you'll have somewhere between 15, manual machine that is, 15 and 20 levers, knobs, buttons, hand wheels, things that you use to control this machine. I drew them with only 6 because I'm not going to draw 15 wheels on these things or something like that. I'd spend all day doing artwork. That's not very good. But you have 15 to 20 different controls on this machine that a machinist has to know how to use, and they come second nature to them after a little while. It's just like a chef in a kitchen will have, you know, 20 pans and 30 knives. He knows each one by, you know, what it cuts like and which ones need to be resharpened and how they feel and when to use them. Well, the same thing for a machinist. You get real comfortable with your machines and you know how to use your 15 to 20 levers and all that kind of thing. Now, with that many levers, each one's got more than one position. So you've got to figure, how am I going to use these? Well, to break it down and make it a little bit simpler, I like to call it IPR because it's simple. Inches per revolution. This is how fast your feed rates are as you're turning down the material. A lot of people like to say shaving, you know, you're shaving the material down. But in the machinist world, at least for myself, I'm used to just calling it turning. It's a turning operation. And those are chips. I'm not making shavings per se. Shavings are a different kind of chip that I use for a different process. But I'm turning the material down and making chips. But we use a feed rate that's called inches per revolution, and typically that's in thousandths of an inch. I'll give you an example here. We'll run the machine at, say, 5 thousandths of an inch per revolution. 5 thousandths of an inch per revolution. So each time that spindle goes around, it moves over 5 thousandths. Okay, that's one set category there, if you will. And then we also use, somewhat related to that, is what we like to call TPI, threads per inch. And how many threads per inch are we going to travel across here? And a lot of machines will do a range, but generally speaking, kind of a good average number is you'll have somewhere in the neighborhood of 64 different threads that it'll cut. Something like a 4 pitch, a 4.5, 5, 6, 7, 8, 9, 10, 11, 11 and a half, 12, 13, 14, it kind of goes up, you get the idea, but we've got a lot of pitches. Doesn't go all the way from 1 to 64. There's gaps in there because some of these we just don't use, like something like a 31 pitch thread. Nobody uses a 31 pitch thread unless they're doing something very special. Anyhow, that's something different for another day. but about 64 settings for this here. And that's your threads per inch. And then the other thing that we like to talk about is your RPMs, revolutions per minute. Most people know what RPM is, and there will be levers associated with that. So you've got here 15 to 20 levers with somewhere in the neighborhood of maybe 70 different settings for controlling your RPMs, your feed rates, and your threads. Where am I going with this? The point I'm trying to make is that there are a lot of connections here between gears and levers and feed shafts and all these things that get worn over time. They begin to break down, they wear out. That's just the way it is. You can minimize it, but you can't get rid of it completely. You can't avoid that. We haven't learned the laws of physics that allow us to do that. So in the real world, this is how it happens. All I'm saying is that there's a lot of opportunity here and up here for things to go wrong on you. And with, by wrong, I mean just simply not work. They will not work. The machine is broken. You have to tear it apart. It's going to take you 2 days to get this animal taken apart, find the problem, and then who knows how long to do the actual repair, to either find the parts or make the parts, and then to install them there. And I'll tell you, putting these machines back together isn't always a cakewalk either. A lot of times that's a whole scenario of its own, and people get a bit frustrated and angry with each other. What do you mean you can't find that screw? I put it right here. Yeah, well, you went and cleaned up after me, so I don't know where you put it. And blah, 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 on they go. And that, everything goes to hell in a handbasket just about. With now, when these things, when an old machine goes down, and each one is different, that can create mayhem in a shop. And I can almost guarantee you it's going to give you late deliveries, cost overruns, and frayed tempers. Okay, but if you buy new machines, if you buy machines that are all identical, then that simplifies things tremendously. And it makes it a lot easier to keep that shop going and to get your deliveries out the door on time, to maintain your quality and your production standards. One other point, I didn't think of this until just now, but it also means that if you run these machines here and happen to be every so often running the same product over and over, you could give it to this guy. Let's say it's product A. You give product A or part A, whatever, to this guy up here to run, and you watch how much tools he consumes and how long it takes him to get it done, and the quality that he puts out. Then you do the same with the machinist on this one and the guy on this one with the same product line. This one, this one, this one. You know where I'm going with this. You can tell very easily who's running efficiently and who is not. And it's not necessarily who gets the job done the fastest or who does the quote-unquote best job, because his tool costs might be way up and that might not be good. But you get to find out who's running most efficiently and basically making you the most money. He'd be the one to ask questions of. Actually, you want to ask questions of everyone. Find out what they're doing, why they're doing it that way, what they think, what could improve it, all this. But you've got some way of quantifying your productivity and your costs. And that helps out with the bottom line, because then it makes it more predictable when you plan these jobs out and you say, oh, last time we made 20 of these, now we've got to make 100 of them. What do we do at that time? How long is it going to take to make them? What do we do with our tooling costs? Do we multiply it by 5, 5 times as much to get 5 times the product? Or do we just need to double it? How are we going to do this? You can look at the times and the costs associated with each operator on all of these identical machines, and that makes it a lot easier to figure out where you ought to put some emphasis and what things you need to watch out for, what potential problems you'll have. Anyhow, I think that does it for my tale of 6 lathes. If there's anything I missed here, I'll bring it up in a subsequent episode. But I hope that gets you thinking about the benefits and sometimes the drawbacks to having multiple machines of the same model or of different models. Thank you very much. God bless you. Have a great day.